Hello everyone. Today we will discuss about the constraints of dynamical systems. First we will define that what is a constraint. You know that constraint is a restriction or a constraint limit the motion of a dynamical system. Constraints are applied on the dynamical systems. It is always that the degree of freedom is reduced. So in classical dynamics we consider basically two types of constraints. Number one is the holonomic constraint, and the other is non-holonomic. Holo means complete. Okay, now we will understand the holonomic constraints and non-holonomic constraints by some examples. Now suppose the first example is here. Let us suppose that a particle is moving on the circumference of a circle. It is a two-dimensional case. This is the origin of the circle, and let us say the radius of the circle is r. Then for this mass m, which is moving on the circumference of the circle, you can write equation x square plus y square equal to r square. So here you also know that the degree of freedom is 1. R is here constant, and either x is dependent coordinate or y is dependent coordinate. So there is only one independent coordinate, so your degree of freedom is 1. Constants in terms of equation form, it is like x square plus y square is equal to r square. Maybe example number 2. Suppose this is the case of a simple pendulum. This is your y-axis, this is your x-axis. The mass of the bob is m, and let us say its coordinate are x and y. This is your origin, and the length of the string is L, and that is constant. So for the simple pendulum, your condition will be that your x square plus y square is equal to L square. So again you can write it in equation form. So here you also know that earlier by earlier examples that the degree of freedom here in this case is also 1. Now we will take the third example. Suppose here is a spherical pendulum. In a spherical pendulum we will consider 3 axes. This is your x-axis, suppose this is your y-axis, and this is your z-axis, right? And a bob of mass m, it will have, for the spherical pendulum, it will have, you know that it will have 3 coordinates. So here the condition in this case will be x square plus y square plus z square is equal to L square. Here L is a constant, so you know that here degree of freedom is it is 3 minus 1 equal to 2, because here one restriction, that is L is constant and the number of particle is 1 and it is a three-dimensional space, so it will be 3 minus 1 equal to 2, right? The other example we can take, we have already discussed this example. Again we can discuss it. This is a wedge block problem. Here let us say this is a wedge and the angle of the wedge is say theta. This is your x-axis, this is your y-axis. In clockwise direction it is making an angle of theta. If you consider its angle from the anti-clockwise direction, then it will be 180 minus theta, right? There is other block of mass small m and the wedge mass is capital M. Earlier we have discussed, let us say the coordinates of mass m at an instant are x1, y1, and we also know that if the small m mass moves in downward direction, then the mass of the wedge move in backward direction, or it moves in xo direction. Okay, so let us say at any instant its distance, its vertical distance from OY axis is say x2. Now here in this case the degree of freedom, you know that here your degree of freedom is, it is 2 into 2 minus 2 and it comes out to be 2, because in x1 y1 coordinate your one coordinate will be independent coordinate and other will be dependent coordinate. Similarly, as your block of mass small m moves in downward direction, so your x2 is also changing, so it is also a dependent coordinate. So here the number of particles are 2 and here restrictions are 2, so the degree of freedom will be 2. All these problems are related to holonomic constants. Now what are the non-holonomic constants? It is very simple to say that those constants which cannot be written in the form of holonomic constants are called as the non-holonomic constants, or the equation for non-holonomic constants will be in equality form. Here we will take some examples. Example number 1. Suppose a particle is moving inside the surface of the sphere. Say this is your O, this is x-axis, this is y-axis, and this is z-axis, and this is your mass m. Let us say O is the origin of the sphere and its radius is capital R. what I have said that a particle is moving inside the surface of the sphere. So the equation for this condition will be x square plus y square plus z square is less than or equal to r. So this is square plus z square is less than or equal to r. So this is in equality form, right? So this type of problem will be treated as non-holonomic constant. The other example which I can take, let us suppose a particle is placed on the surface of a sphere. This is the mass of the particle, and there are three axes. Again, this is your x-axis, this is your y-axis, this is your z-axis. This is origin. Let us say the radius of this sphere is r. Now if this particle m moves from the surface of the sphere, then you know that it will be the condition for here will be like x square plus y square plus z square is greater than or equal to r, because the condition x square plus y square plus z square equal to r will be when it is moving on the surface of the sphere, but you know that after some time it will leave the surface of the sphere. Okay, so in that case your condition x square plus y square plus z square will be greater than r. So again it is a non-holonomic constant condition, right? So we can say that the non-holonomic constants are those constants which cannot be written in the form of an equation, or non-holonomic constants are written in the form of inequality form. Thank you.